So, hi, I'm trying to.
Hi, everybody. Good afternoon. Thank you all for being here today, and thanks everyone online as well. Today I get the pleasure of introducing Dr. Shimon Wdowinski, one of our own here at Florida International, but been pretty well traveled, originally from Israel, did some graduate work there, as well as in the U.S. at Harvard before and out west to work in San Diego as well. And yeah, done a lot of things here, but leadership team of the sea level around unit here as well too. So some neat stuff and pretty diverse background. And today I get to hear a little bit about earthquake work. And yeah, excited to hear his talk. So without further ado.
All right, thank you. All right, so today I'm gonna talk about what it says over here: climate control on earthquake clustering along continental transform faults, evidence from the 120,000 years paleoseismic record of the Dead Sea Basin. So since I teach some classes over here, and I know that many of the students are not familiar with some of the terms over here, I will go slowly through some of the concepts and things that related to earth sciences. So like I'll explain what is continental transform form and earthquake clustering. So be intimidated yet. So the thing is that we're going to talk about climate control. When we talk about climate, I'm not talking about climate change that everybody now very concerned of the past 100 years or 200 years since the industrial revolution, but I'm talking about the record of climate since the last few 100,000 years, and when we have the ice age and glacial and interglacial. So this is the level of the climate that I'm talking about. Now, earthquake clustering, so we can have clustering in time and space. Here I'm talking about clustering in time, means that sometimes we have periods we have higher number of earthquakes versus periods that we have less amount of earthquakes. And all of that actually we find from a study that we did over here, the Dead Sea, which is running along the Dead Sea transform fault. All of that will be explained. This is a joint work that is supported by two programs, the NSF, National Science Foundation, and BSF, which is a Binational Science Foundation. So we have a team from Florida International University, which includes myself, Michelle Higgins, Mita, Uterman, that doing some of the modeling, we'll see that. And the team from Tel Aviv University that include Ishmael Marco and Anne LeBlanc. And also we have a third institution, which is Tongji University from China, that Ian Lu, who was a postdoc at Tel Aviv University, and he did a lot of work. So he's part of this team. So what I'll have the background include introduction about earthquakes, earthquake records, then about the Dead Sea, the tectonics, seismicity and structure, then lake level changes, see how they connect with one another, and paleoseismic records from the Dead Sea, onshore from outcrops the past 70,000 years, and offshore from boreholes of the past 220,000 years. And then time series analysis, correlation analysis, some basic things with when we have numbers. And how do we explain that, that we have climate control on earthquake clustering? And then a summary. So earthquakes, earthquake is it's a known hazard, is one of the most devastating natural hazard. It can by itself cause a lot of damage. Told here we see example of a house, apartment buildings that collapsed during the earthquakes in Turkey just a few years ago. And also can generate other hazards like tsunami, landslide, and all of that can cause a lot of damage and life toll. On the right-hand side, you can see some of the most devastating earthquakes of the past century, since the 1900s. And top of the list, you may remember the Haiti 2010 earthquake that caused the death toll of about 300,000, although some estimate revise it down to 220,000, but it's up there. And then there were two very devastating earthquakes in China, Yuan earthquake in 1920, and then Tangshan in 76. Again, more than 200,000 casualties. And if you remember, you may be young, but some of you, that in Sumatra 2004, there was a earthquake that triggered a tsunami that caused deaths throughout the Indian Ocean, all the way to Africa. So there were also more than 200,000. But one thing we always say in our field that earthquakes don't kill. What kill are the buildings. So it's important to build correctly. And that's different between a developed country and developing country. That in developed country, we already have infrastructure that it's much better, can withstand earthquakes compared to developing country where we have all of these damage. So why earthquake occur? So this is a basic concept that it's already more than 100 years old. It's called the elastic ribbon theory that was introduced by Reed in 1910 after the San Francisco 1906. There was a very devastating earthquake in San Francisco. And what happened is that he didn't know about tectonic plate motion at the time, but he measured and saw that there were movement of blocks that it can move over time, and that can take many years, 100 years, 200 years. And they accumulate stress. And at some point, the stress cannot really sustain. Then they yield, and there is a rupture. It's like if you take a stick, you bend it until some point it breaks. And this is called the elastic ribbon theory. And basically, there are three stages: the interseismic, the slow accumulation of stress, or displacement, or strain. There are different things that we can measure. And then they reach the yield stress, then it rupture. We have a stress drop. This is the release of the seismic wave, and then there's an adjustment period called the post-seismic, and then again, accumulation of stress. So these are the major things, how earthquake work. So according to that, we have a cycle, earthquake cycle, basically deformation cycle. So in theory, that at least according to the elastic ribbon theory, it should be cyclic, and we should expect to have earthquake almost every certain amount of time. Maybe 100 years, depending how fast these blocks are moving, maybe 5,000 years if they move slowly. You can see here, this is the earthquake, this is the accumulation of displacement, this is the strain of the stress that's accumulated during the interseismic period, then it drops and accumulated again. So this is in theory, but in reality, we don't see that. In reality, we have a period that we have many earthquakes, and then the quiescence, and then some earthquake and more quiescence. And this is, some people suggested, this is going to be, call it the earthquake supercycle. So if over here we think we need observations of a few hundred years, in this case, we need several thousand years. So we need to get information how to study long records of earthquake. And we study earthquake nowadays, we measure it, we call it this instrumental period. We use seismograph. Seismograph, you can see example over here, that it's a needle that moves, that's like in the movies, nowadays it's more electronic, we don't, but basically we have a sensor that measures the movement of the earth. You can separate that, and we do it in 3D. But this is the first seismogram was just measured 136 years ago. That was the first seismogram in Potsdam, in Germany. So we have a record of 140 years at the most. Also, the first period was the measurement weren't that accurate. There was the instrument very good. Nowadays, we can pick up a lot of, they are much more sensitive. So we need to extend this observation period. So there are different ways of extending. Some places where we have historical documents or archaeological site, we can extend it for thousands of years. So this is an example of a document that was found in Cairo in a synagogue on top of the ceiling, on top of the ceiling of the synagogue. They used to put document that not considered holy. You cannot just saw them. There is some problem, so it's called the Cairo icon, and tens of thousands of documents from different periods. And this is in this particular document, from 1033, was written by some guy who lived in Ramla, which is in Israel. Described great detail the terrible effect of earthquake and its aftershocks. So this is an example of historical document. In another place, we can have what's called seismoarchaeology. This is again from Israel. This is a Crusader castle that built on the fault, the Dead Sea fault. We'll see more about it. And show a displacement of 70 centimeters of the walls. So this is example of, and we know from a document exactly when it happened. It was at 1202. So we can extend this record where we have documents and archaeological site, and it's in the Middle East, in China, up to 2,000 or 3,000 years. And here we can see here that what we like to call is like the propagating events. There is an earthquake that was over here in the north, and then it triggered another event and triggered another event. So this helps us using this historical document and archaeology to study the relationship between earthquakes. So they give us, but then there are periods of lack of information. Like here, there were no people in the desert. So it's important information, but doesn't give us the whole picture. Then we can go to another method, which is called paleoseismicity, where we can have trenches. So take a tractor and it can trench. This is a pretty wide trench from Japan. And we can see from the rock, the displacement between rock units when there was an earthquake. This is the example from California, where it's hard to see in the black and white, but the people who interpreted, they found that there was a displacement over here. So there was an earthquake over here for the event, and there was another displacement. You can see here between this blue unit was displaced over here. So in this way, they can pick up records. We go back to 7,000 years, maybe 10,000 at most, but it extends the record. So using this method, that's how they know that in California, the repeat cycle of earthquake is about 165 years. The study of trenches over there in California. And the last big earthquake in California, the big one in Southern California that affected Los Angeles was when? Anybody know?
1857.
Very good, Ben. So 1857 plus 165 dates take us to now, to present day. So when you are living in Los Angeles, when there is a ground movement, people ask, is it a big one? Because they have all the time small ones. So this is the way how we can get information. So it's very important to get the longer record. But we know in other places that it's not always at 100. It's 165 plus 100, maybe 85 years. So it may be going to take another 100 years. So we need to look even at longer record. Longer record can get from geological observation. This is when we have turbidite. So turbidite are these flow of sediments in the ocean or lakes, that if there is an earthquake or something that the sediment accumulate on the slope, like we can see over here, and if there is shaking, the sediment can flow down, roll down. So it's a flow dynamics, and then they accumulated somewhere. And if we take either see them afterward exposed in an outcrop, as we can see over here, or take a core of sediments, and we can see when there was an earthquake. The problem is the geological timescale, it's millions of years, and the separation between events, it's very hard to find that. So it's like, we don't have a very good record of that. By the way they found that turbidite generated by earthquake was in the 1950s, when there was a communication between Europe and North America was by a cable on the surface of the ocean, and at some point it got disrupted, and they didn't know why. They went to the record, and we found that it was when there was this movement of turbidite in the Atlantic. So basically, it cut the cable. So this turbidite can still cause the disruption. Nowadays, the Russians are doing it, the Houthis are doing it, they cut these underwater cable, but it can happen naturally, so it's important to watch them. And where we going is the earthquake record from the Dead Sea, which is, we can see it both onshore. We can see example of, it's like a turbidite, we call it seismite over there, but basically it's a movement of layers. And you can see how it looks very pretty when you go over there. So this is a layer sediments that were accumulated somewhere on the lake over there, and they were disturbed by shaking. And we then went and extended it to 220,000 years using observation from borehole. So this is the longest detailed record of paleoseismic events.
Where is the borehole taken exactly?
I will show.
In the Dead Sea or in the Mediterranean? In the Dead Sea.
Yeah, I'll show it. We'll get there. If it just transition. Now we're going to the Dead Sea. So the Dead Sea fault is a tectonic plate boundary separating between two plates, the Sinai plate and the Arabia plate. In the bigger pictures, we have three big plates. We have the African plate, also divided. Then we have the Arabian plate and the Eurasian plate. And there are two in the area in the Eastern Mediterranean, there are two smaller plates, the Sinai plate or subplate and the Anatolian block. And there are three major faults that we call it continental transform. The Dead Sea fault right over here. And then there's the East Anatolian fault and the North Anatolian fault. And the major plate tectonic picture is that the African plate is moving northward and colliding with Eurasian. So that's where we have subduction along it's called the Hellenic and Cyprus arc over here. So the African plate is moving downward. But on the eastern side, there is no subduction because it's continent cannot subside, the oceanic plate can subside. So we have over the collision, the Zagros Mountain, and in some places is a motion is transferred, like the Dead Sea Fall. It transferred from opening in the Dead Sea to a collision in the northern part. And what we see over here is that they call it extrusion of the Anatolian plate or block to the west, as it's squeezed between the Arabian plate and the Eurasian plate. And the recent earthquake in Turkey and Syria were on the East Anatolian fault, right in this area. So they saw the picture of the buildings that collapsed, and there were a lot of devastation over there. In 2000, there was another earthquake, devastating earthquake in Izmit. It was on the North Anatolian fault. So this area is tectonically active. Now we call it transfer fault. The transfer fault was first introduced when studied the tectonic of the ocean. So in the ocean is open, we have mid-ocean ridges. And sometimes there is a break between them, and these are called transfer because it transfers the opening in this side to the other side. In the continent, it's a little bit more complicated, but still we call it continental transform fault. And one of the best example is the San Andreas fault that transfers the motion again from the opening of the Gulf of California, of the Sea of Cortez, northward all the way to British Columbia and then to Alaska. So this is the transform fault. And what we see over here is that the Dead Sea fault is associated with seismicity. So there are a lot of seismic events. The most recent were in the Gulf of Aqaba, of Eilat, but there is a sporadic seismicity. It's not as active as the San Andreas fault because the rate of motion is much lower. It's about 5 millimeters per year, versus in California, we talk about 35 millimeters per year. So the rate of seismicity is much higher in California. In North Anatolian fault, East California is also about, North Anatolian fault is about 25 millimeters per year, and here is about 12 millimeters per year. So we tend to have more seismic events, so seismicity, than the Dead Sea fault. And so this is instrumental observations. This is a historical observation that we saw. We have this sequence of earthquakes. Some places we see repeated earthquake every 200 or 300, but then there's a break here, a few hundred years with no earthquake. So we need to get more information about that. So that was the Dead Sea fault. Now we go to the Dead Sea Basin, which is the Dead Sea. If you didn't know, it's the lowest place in the continental Earth. Its depth is 400 meters below sea level, but actually it keeps increasing the depth because the water, there is a lot of water loss over there. Working a little bit, but why open this big hole in the crust over there? We call it pull apart basin. Basically, there is two faults, track slip faults, that horizontal faults that they move. They are more or less parallel to one another, and because of the geometry, there is displacement over here, and a basin form. So we can see here we have the northern movement of the Arabian plate with respect to relatively to the southern, and we have one segment of the strike slip, the horizontal fault here. The second one is over here, and on the side we have also normal faults that because otherwise we're going to have really very deep and steep faults. So there is erosion, there's all the things. So and when there is a big hole, usually erosion brings sediment over there, and it's a very deep. There was a drill hole that went down to 8 kilometers and still didn't reach the basement. So we know it's deeper than 8 kilometers. Now it's a terminal basin. It means it's eternal drainage basin, and as a result, we have a lake over there, and it's a unique place. The salinity there is so high, is 35% versus 3.5 or 35 per mil in regular ocean. So it's 10 times saltier than ocean. So if you go over there, you basically can just float. Anybody visit the Dead Sea? Did you experience that?
Sure. Oh, absolutely.
What happens if you have a wound?
It's not
That
pleasant.
hurts.
It's not pleasant, yeah.
So, and you can see there is it's so salty, so there is actually, salt can actually mineralize on different places. So it's a very fascinating place to visit. Now the Dead Sea is losing water in very rapid rate, about a meter per year since the 1970s. So we can see the area of the Dead Sea is shrunk from 1931, which included both the northern basin and the southern basin. And then we have only the northern basin since the 1980s. And the reason that it's losing so much water is that one, there is water diversion for agriculture, for human consumption farther north. So both Israel and Jordan use the water. And there is the salt of the Dead Sea is very rich in minerals, and it's used for different agriculture, for industry. So there is these what they call they are drying basically these pools, hydration pools that they bring water from the Dead Sea, let it get dehydrated and to get the mineral, and then they extract the mineral out of there. It's done both on the Israeli side and Jordanian side. You can see that it's been increased over time. And so we're gonna slowly but surely losing the Dead Sea. And there've been different suggestions how to save the Dead Sea and to have the canal that connects the Mediterranean over there, or the Red Sea connect and to bring water. But there is a lot of issue associated with that because the regular ocean water or Mediterranean water are not salty enough, and what as a result going to generate a gypsum layer of gypsum as they interact with the salty, very salty water of the Dead Sea. So the depth of the basin over here in the northern basin is about we have 300 more meters, but as it gets saltier and saltier, the evaporation slows down. So that the geochemists suggest there's going to be some kind of a steady state, but still we are losing a lot of water. And another thing that it's not really related to that, but it's a very interesting phenomenon which I worked on it in the past is sinkholes. So as the Dead Sea lake level drops, the Dead Sea level drops, they formed sinkholes along its shore. And they start forming actually in the 80s, but mostly in the 90s. And there are more than 6,000 sinkholes, and they keep forming at a rate of 400 per year. And the reason for that is that there was a period that along in the Dead Sea, that was a layer of salt that was deposited. It's at depths of maybe 30 meters below the surface of the shore. And when the sea level was high enough, it was washed by brine, by salty brines. So it kept its formation. As the Dead Sea level dropped, this layer is being washed by fresh water. And they form a lot of dissolve very quickly and form these sinkholes. So these sinkholes develop fast in years and can collapse very quickly. Here in Florida, we have a problem of sinkholes, mostly in Tampa, in that area of Orlando. But here in Florida, the sinkholes are in limestone. So it's not that they're forming that quickly. It means they formed over a period of 10,000 of years and been cavities there here in Florida, but are covered by soil, call it the caprock. And as we make changes to the groundwater, the caprock or the soil loses its cohesion, and then it can either subside or sink. And we have the collapse, a sinkhole collapse. So it's a different mechanism, but on the surface, it's we have the same result of materials that collapse into the subsurface. So this is the Dead Sea today. In the past, the Dead Sea level fluctuated. there were periods that it was much higher than today. So today we say it was minus 400 or 450, maybe it will continue to fall. But there were a period of, we call it the Lake Lisan, about 20 to 30,000 years ago, that the lake level reached minus 180 below sea level, so about almost 300 meters higher than today. And so this is called the Lisan lake. And it covers, so this is the Dead Sea drainage area. You mentioned that it's a terminal drainage. It's all in, there's no access to the Mediterranean or to the, so all the water actually reach over here. And during the Lisan era, the lake covered a much wider area. So it's the Lisan covered the time area of about 200,000 square kilometer versus nowadays, which about 400. So it was 5 times wider and deeper.
Did it ever connect to the, did it connect to the Gulf of Aqaba?
No, it was never connected. Actually, it became very salty when it was connected during the Pleistocene to here, to the Bay of Haifa. This area is a low topography, and during that time there was opening. And it's not that it connected once. Also, the Mediterranean was at one point disconnected from the Atlantic Ocean. It was a formation of a thick salt layer over there. So it's not connected once, because if once you have maybe you fill 100 meters of ocean water, but when it evaporates, you are stayed maybe with 1 meter of salt. So there is a multiple events of flooding and evaporation. So it's a multiple process, and that result in this salt layer down deep in the basin on the Dead Sea. Like I said, it's up to 8 kilometers. Some of it is salt layers. So we mentioned about the Lisan Lake. So as a lake, it has also collected sediments, and we see here a picture of this, the sediments. So this is this mountain over here. Can anybody recognize that? It's a historical site in Masada. So this is Masada. It was there's a very interesting story here about the rebellion of the Jewish state versus the Roman Empire that ended over there. But anyway, we can see this is Cretaceous rock over here, and the lake's Lisan sediments are the white ones. And actually, they're not completely white. They have these lamina that they show that actually interfaces between aragonite, which is a form of calcium carbonate, like limestone, but it's slightly different. And the greenish is clay. And these are seasonal. And we call it varves. And there were studies that people counted the varves and did dating, and they found that it's can go year by year. So you can actually measure year by year the position of the layers. So what happened is that during the rainy season, the clay were accumulated by floods that came from the mountains. And during the dry season, there was a chemical deposition of aragonite. And we have this sequence over here. And what happens, this is very sensitive to strain. And we can see that in many places over there in the Lisan formation, we can see, this is just an example of these cliffs, very nice, and it's easy to work. It's very soft rock. And we can see these deformed layer, which we call seismite. My colleague Shmuel Marco, he did his PhD 40 years ago and he worked on that since then. He is very knowledgeable about it. And so we work together about this. And we can see here like two different events, one on top of the other. Here we see a smaller event. Here we see another event. So these are all different type of shaking. And this is an example of what is Lisand formation. So we have this nice lamina, and then there is a shaking, and we can see this breccia shaking as a result of this. And this is an example of a seismite layer like that it's all broken. Here's another example of a nice seismite that can go for a pretty long distance.
So Shimon, have those been disturbed by the actual ground shaking, or is that some sort of compressional deformation that you see in that?
Yeah, so these are the good points. So some of them are deposited just by the shaking, so in the same location. But many of them, what we see over here is they've been transported down. So there are small gradients and they can transport it. So we have here a beautiful fold and truss belt, like
It's like a duplex.
yeah, like in the Alps, yeah, but much smaller scale.
Shimon, what's the scale of each of those curves? Like meters or?
So here you can see a person. So in this case, the whole layer is about a meter and a half. So these you can see that we have like, but it thickened because originally it was much thinner, but it traveled and accumulated. So there is a thickening of this the section, the sedimentary section.
Is that one single event?
This is, yes, this is a single event here.
So all that deformation occurred maybe over a day.
We can see here we see in this case over here it's like two events, the same location. So these are very dramatic, but you can see some places are not so dramatic. So we have.
Did you say they're salt and clay, right?
Aragonite?
I mean, are they salt or?
No, the aragonite is like limestone. It's calcium carbonate, and the clay.
Clay, yeah.
So just to show that this is related to shaking. This is in this example, we can see that it happened during the sedimentation. So we call it sedimentation faulting. We can see this section here on the right-hand side. We can see the continuation of it on the left-hand side, but displaced downward. You can see this relatively thick unit here is displaced downward over here. This unit is displaced down over here. We can see this almost the brown, dark brown over here. But further up, there's no displacement. So we can see that the area over here, there was a drop of the left unit. And there is accumulation of breccia over here. So this happened during this faulting event happened during the sedimentation. Now, how we can explain that? So my colleagues at Tel Aviv University, they've been working on the physics of that, and they adopted they did some numerical model and used a very interesting name. It's called Kelvin-Helmholtz shear instability. So basically, we have two viscous fluids with different properties that being shaken, and as a result, they move. Oops. So you can see the instability moves here. And then there is also like a wave coming on top of it, and we generating of pressure. So in this particular example, we can see that there is a breccia formation from turbulence to breccia. So think about these sediments that they were like a mud, or they're soft, but not completely fluid. They have some cohesion, so they still can move in a cohesive way together. And then they reach, they can be like overturning and forming a breccia.
And so, sorry, but in that equation there, so really what it is even if it's a similar material, it's the bulk density that's a little different. You got a thicker, a denser layer overlaid by a softer layer. Is that the density of that?
So the viscosity here, so we have the density, so the density lighter material on top of heavier material. And the viscosity is, there is a viscosity difference between. So the upper is less viscous than the lower one, so it can flow faster. So here are some results from numerical experiments that my colleagues did. So this is according to this condition at different time step. So this is, it depends what is the thickness of the experiment at 0.3 second. As it progresses, you get different results. And we can see here example versus some of the observations. They call it, this is breccia, that we have a lot of that. We can have situations which they call coherent vorticities that have been observed in the field and also generated by the simulation, and linear waves. So this is the amount of deformation is low here and increases upward. And the physics of that rely on two, in fluid mechanics, we have these numbers that we take, it's non-dimensional. We take this number, one is Richardson number, one is Rayleigh number, and they studied the different, when do we see the different phenomena, and they separated it. So we get a pretty good understanding of the physics of this phenomena. You can see over here. Now, this is what we observed so far was on the shore. Now we want to extend it to go also offshore, and going to take it even to a longer period to the past. And this is the borehole. You can see over here. We call it the depot center. It's the deepest part of the Dead Sea. And in 2011, they brought a barge. There's a international Continental deep drilling project, and this was the core of this number. And they recovered 455 meters of core, and it was almost continuous record for the past 220,000 years. And this is just to give you an example. This is the bore was over here, and this is the slopes over here, and so we get pretty good idea. So material comes not necessarily only from the position in the Dead Sea, also it actually there's a debris flow or there's troglodytes that coming down from the slopes farther up there. So this is the 155 meter of coral with different lithologies. But over there, I mentioned the postdoc who is now a professor in China. That was his postdoc. He analyzed very carefully this core, and he identified events where we see seismites over there. So this is when there is no deformation, but some places we see there is deformation and some intense deformation. And so this is Jean Lu, very thorough work. And that's how we got this very the longest record of detailed earthquake activity. So what we see over here when we look at a few thousand events, and when we plot all of the events, we see the period that many events, like here, around 20, 25, 150, and the period with less event. So we call it, this is clustering. So that clustering, we can even look at it at different time scales. When we look at the 100,000 years, we see clustering. When we look at just 22,000 years, we see, again, clustering. There's clustering over here, clustering over here. And even when we zoom in to the thousands of years, we see clustering over here. So we can see this clustering of earthquake at different order of magnitude. Now, what do we do with that when we have such a record? Anybody have time? So we usually, if you take my course, you know, you do time series analysis, okay? But when with this record, it's very hard to take to do time series analysis because you have 1 and zeros, a lot of zeros and ones. So it's hard to do that. So the way to overcome it is to bin it, to put it in bins, and to calculate how many events per bin. So if we put per 1,000 years, we can see that, again, we see the clustering, but again, we have still a lot of space with no earthquakes over there. When we look at every 1,000 years, this is 100 years, this is 1,000 years, and this is 10,000 years. We see similar picture, but we can analyze it now because we have more or less continuous record. And when we do time series analysis, spectral analysis, we look for dominant periodicity, and analyzing this, the record of with 10,000 years, it yielded 55,000 years and 110,000 years. It's multiples because the record is 220,000 years old, so these are multiples or division of that. When we look at this, we see predominant periodicity also of 14 and 20,000 years. And does this number resonate with you? Anybody took my class before? Milankovitch cycle. So Milankovitch cycle have some of these periodicities, eccentricity, there's a change in the electricity, 95 to 136,000 years. Then we have obliquity and precision. And we see these similarities, because it's not exact, but we see these periodicity actually exist over here. So why do we have that in the record of the earthquakes? And so we can look to see what fluctuated as a result of this cycle. Actually, I need to go back, and maybe some people who didn't take my class don't know what is Milankovitch cycle. So Milankovitch cycles were these. Milankovitch was a geophysicist who he realized that there is cyclicity in the cycles, different things in the Earth, and he attributed it to changes in the astronomical position of the Earth, whether the orbit changes from more elliptical to spherical, or the motion of the North Pole, its position in space. He attributed it and he calculated the time of that. So this is the Milankovitch cycle. What can contribute to that? So we can see that one of the suspicious, actually, I suspected it was related to sea level, because sea level, global sea level has this periodicities, but actually what's more realistic is the lake level of the Dead Sea. So the lake level fluctuated due to, because it's a terminal basin, due to the rain. So the climate the amount of rain that was available over there in the basin. And we can see it's basically a mirror image of the global sea level. So we have the Dead Sea level. During the ice ages, it was high, where the global sea level was low, because there was more rain over there, in the Dead Sea, and vice versa. Now in the glacials, we have high sea level, and the Dead Sea is very low. Now, so we did a correlation analysis between the number of events per 10,000 years. We did with different levels, but we can see that look of the age, the mean lake level for 10,000 years versus the number of earthquakes per 10,000 years. And we get this nice correlation over here, suggesting that there is a strong correlation between the earthquake frequency and lake level. So how can we explain that? So possible explanation for this correlation is the frequency of earthquakes changes with lake level. Does it make sense? We'll find out. Yes. The sediment response to the shaking can be different if you are in under high lake level or low lake level, or the area of the volume that is available for the material to respond to the shaking also changes. So when you think about the climate and earthquake, people say no, they're not connected, because the tectonics, earthquake formation is within the Earth's interior. So in the Earth's interior, indeed, the plate move, the momentum move without much response to what happens on the surface. So this is the strain accumulation, the interseismic rate. However, the release of the stress can be very much affected what happens on the surface. So we have the release, the timing is tectonic stress is accumulating, but the release can happen due to surface load changes or pore pressure changes. And this is how climate can impact earthquakes. And so I mentioned pore pressure changes. So pore pressure is this the amount of water that actually in the pores. And think about it, we have fault, and if it's very dry, it will be more resistive. If there's some more water in the pores, it may be lubricant and basically increase the probability to reach a failure. In structural geology, we use this figure. This is looking at the stresses. So we have stresses in the crust in 3 different dimensions and orientations. Now, if we increase the pore pressure, it moves everything to the left toward the failure, and it causes earthquakes. So this type of earthquakes due to pore pressure increase, it happens a lot when we build a reservoir, like Lake Nasser in Egypt on the Nile. It generated a lot of seismicity afterwards. That's what happens a lot now in Oklahoma, which is one of the seismically most active area in the United States, where the fracking, after fracking, they put the wastewater in the subsurface and causing earthquakes. So Oklahoma become very seismically active due to fracking. So when we look about what happened along transform fault, there were several studies that looked at it. This is in California. This is Salton Trough in Southern California. And people who studied that, we can see a couple of studies and notice that the major earthquake on the in this segment of the Southern San Andreas Fault occurred when during high lake level in Salton Trough. So now we are in a dry, so it's less likely to rupture now. Okay. Another study looked on the Dead Sea, and they calculated how the earthquake occur with the fluctuation of the lake level due to this change in the pore pressure. Now, what we are doing is we are looking both at the pore pressure changes, but we're also looking at changes in the normal load. So as we have 100 more of meters, we have much, it's the load, the hydrologic load is very heavy, and it can increase what we call the hydrological load. And what we see in the Dead Sea, we have strike slip faults over here and normal faults. And when we increase the hydrological load, we can bring these normal fault closer to failure. So basically, we can activate the normal fault system, and pore pressure can increase both of them. So initial modeling that we did, we looked at what happened during low lake level, and then we increased the load, just high water level, and it's activated the normal fault over here. So just to give you, this is strike slip fault over here, and these are normal faults. So this is more idealized situation. And when we change the pore pressure, we have activating both fault systems. So this is a preliminary result. Now we're working on more sophisticated models using, that was in boundary element. Now we're using finite elements. And here again, we look at the two strike slip fault system with normal faults. And when we, this is a two-dimensional, this is the motion in the y direction along here. And we see also some changes in displacement on the x direction. And when we look at three-dimensional fault, which takes a lot of computation, we see similar results. This is just the beginning of this work, and we'll take into account also pore pressure changes and load changes. So another explanation is sediment response to shaking. This is our group at Tel Aviv University. It studies the effect of different geology in response to hydrological load. What happens if we have Newtonian flow? So this is type of the rheology is how the material behave in response to stress. So we can see that if we have viscoplastic flow, which is a different characteristic, we can have different things. So we keep working on that. And another thing that we are looking is about how sediment availability to shaking. So high water levels means that we have more area exposed. We're underwater. They can contribute to the sedimentation at the depocentre. And so we can see the different gradient, different thing. We study that too. So took almost an hour. So just to summarize, we have here the longest paleoseismic record of 220,000 years. From the Dead Sea Basin. It provides a unique opportunity to explore both earthquakes, super cycles, and climate impact of earthquake temporal clustering. And we provided explanation that can be either tectonics, the faulting, both strike slip and normal faults, activation of the secondary. And the sedimentary explanation is the impact of seismic generation and seismic rheology. So just to acknowledge, we got support from two agencies, the National Science Foundation and the Bi-National Science Foundation. And the data was we acquired using the ICDP Dead Sea drilling project. Thank you.